Okay, next we're going to extend this idea of descriptions for dimers to multimers, and in particular focus on proteins, because they're one of the more interesting systems that are interrogated using second-order nonlinear optics. And we'll start out with an alpha helix as a model, and then show how you can extend this to other protein structures and macromolecules as well. But the idea is to first start out with a description for a just coherent addition of a whole bunch of different contributions, and we'll focus on the amide contributions because it turns out those have a pretty respectable nonlinear optical response, and they have a lot of key vibrational signatures as well. And then what we will do is use symmetry to take this coherent addition and break it up into contributions for particular symmetry-allowed transitions. Okay, so an alpha helix, if we look down the helical axis, this first amide group sits right there. The next one is rotated all the way over to here, and then the next one over to here, and the next one over to here, and we work our way around. That's now the second turn, and if we ask ourselves what are the, if we neglect this translational component as we scroll down the alpha helix because the distances traveled there are much less than the wavelength of light, then we can really think of this this helical process, this helical response as just being a 18-fold rotational symmetry for each of the individual amide groups. And it turns out in nonlinear optics, if you've got anything higher than 4-fold rotational symmetry, it's equivalent to C infinity. So 18-fold and 4-fold have identical operations and identical character tables as well for describing even-ordered nonlinear optics. But at any rate, we can think of it as this 18, as a summation, coherent summation of each of the 18 different contributions it takes to work your way around the arc, around down the helix. So if we know how to describe the nonlinear optical properties of one amide group, how do we then use that for describing the collective nonlinear optical properties of the entire protein? And I'll show you an example using NLO predict. So what's shown here on the right is the amide group. This is N-methylacetamide, which contains this amide moiety, which is the bond that bridges the poly. So over here on the right is N-methylacetamide, which includes the amide linkage that connects amino acids and proteins. And we can describe the nonlinear optical properties of the amide group. This is the set of all 27 elements for the molecular tensor in the coordinate system shown here, where the horizontal axis is the x-axis, the vertical axis is the y, and the z is pointing out at you according to a right-hand rule. So we can describe the molecular tensor in any coordinate system using this approach. What we really want to do, though, is match it up to the coordinate system in the alpha helix. So they look pretty close. So this is probably a reasonable orientation for describing the amide group in an alpha helix. And if we add these all up together, it turns out to be given by this bottom one, which corresponds to C infinity symmetry. And this now becomes, which is equivalent to C18 symmetry, effective C18 symmetry, this now becomes the nonlinear optical prediction for the alpha helix. And what's cool is if we go in and use NLO predict, what it will do is calculate the amide contributions of each one of these and coherently add them up. And that's what we get down here. And lo and behold, if we get this just right, lo and behold, the beta here looks a heck of a lot like the chi over here. So it's actually doing a pretty good job of describing the alpha helix by just the coherent summation of these individual NMA groups. Okay, so that gives us a handle on pulling out the tensor. The next question is separating it out into the two different symmetry-allowed transitions. And we know we have two different symmetry-allowed transitions because for C infinity symmetry, if we go to the character table, it's the same as C4. C18, C4, C infinity, they're all basically the same. And we have classes that are either A or E allowed based on symmetry. And the A transitions correspond to Z polarized transition moment. So they are going to be the set of tensor elements that end in Z will contribute to the A state, which is the sum state, and that's going to be the state corresponding to the component of the transition moment along the C18 axis here. And we can separate that out into everything ending with a Z must contribute, for example, to the A state. Everything ending with X or Y contributes to the E state. and it becomes fairly straightforward to disentangle those. Boy, this keeps wanting to jump ahead on me. And so if we just write up, we can just separate these out and make hyperellipsoids for the E state and hyperellipsoids for the A state. And if the splitting is, if we can spectrally resolve these, then this set of tensor elements and the corresponding hyperellipsoid and the corresponding unit vector sphere all describe just the A state, and the elements that contribute to the E state can be disentangled and separated out as well. In the limit that we make measurements where this energy gap between, I'm just going to change color so it's a little bit easier to see. This energy, it didn't do it, curse you, pen. This energy gap between states, if that is much greater than the full width half max of the transition, then we can spectrally resolve the A and E state and describe them separately based on this formalism. If, however, that energy gap is small relative to the line width, then we typically can't spectrally resolve the two peaks. And in fact, just what we started out initially, just the degenerate sum will describe the nonlinear optical property of that combined peak, which has the coherent contributions of each of the A and E transitions. This analysis can be directly extended to other secondary structures using the exact same architecture. It's just shown here for the beta sheets. If you look top down on an anti-parallel beta pleated sheet, you have this sort of a structure in terms of the arrangements of the amide groups, where this little block here is this diagram right there that describes those carbons. Actually, I think it's this carbon to this carbon, yeah. And we can, if we turn it on its side, so we see it sort of from the side view, you can see that there really is a pleating in the beta pleated sheets. But it's the same essential idea as everything else. Just describe what the amide unit looks like in terms of its nonlinear optical response, and then do coherent addition and separate out based on symmetry. For beta sheets, there'll be 3 different transitions, one Z polarized, one X polarized, and one Y polarized. Okay, so this is a nice starting point. Again, the symmetry additive model is a zero order model in the sense that it treats every amide group as being identical and neglects coupling beyond just the phenomenological ability to separate things into symmetry allowed transitions. So it's going to do a good job in terms of qualitative understanding, but if you want a full quantitative analysis, then it's wise to perform quantum chemical calculations that include these coupling terms explicitly, as opposed to treating them phenomenologically as in the symmetry additive model.